Right, I think we're about ready to start. So I'd like you to welcome you to the last talk of the day. This is our Wollaston medalist, Richard Alley, talking about crumbling at the edges, ice sheets and sea level rise. Richard.
Oh, thank you. It's a real pleasure. So here is a less teasing title, but either of them will work fine. That was the one I said. So I'm going to give you the work of a large number of people, but they had asked me to focus a little bit more on work with our group. So I'm going to do that as we walk through. There's an ice iceberg to start with. Just for reference, sea level is rising. I had nothing to do with this plot, but here's the data. I spent a while dealing with people who called me up and said, quit lying about sea level rise right there. Then they shut up. But so sea level is rising. If we take this and squeeze it down a little, there's an IPCC figure. The previous slide is more or less that one. And I'm going to walk you back a little bit, show you a little of historical stuff, what we've learned at looking at paleo sea levels in various ways. And then I'm going to walk you forward. But if we walk back, sea level has not only risen, but the rise has accelerated. And that actually is clear. We came out of a little ice age and we're headed into something in the future. If we take this slide and squeeze it down, it is more or less this piece right here. This is a little reconstruction from sea level rise work that various people have done. Kopp et al. Have been important in this one. And this one's actually a trend has been taken out of this. But you see the medieval warm period, the little ice age, and the recent rise. Okay? And we had a little study. This is not important, but it was sort of fun. As you know, we had this little ice age. A few big volcanoes blocked the sun for a bit. The sun was a little dim. And you see around many, many, many glaciers evidence that the ice advanced to a maximum and pulled back. And the amplitude has to be some fraction of the third of a meter of glacier, so 10 centimeters. And when people reconstruct the sea level, what do they see? There's a fluctuation there that's sort of 10 centimeters. That leads to a prediction. Because the water comes out of the ocean and it goes to the glaciers, which are closer to the pole when you make the little ice age. And like a skater pulling in her arms, it spins a little faster. And so there's actually a prediction that comes out of the existence of a little ice age, which is who saw eclipses where over time will have changed. Because the length of the day will have changed just a little bit. And in this paper, which came out last year in EPSL, we tested it and it works. And if that isn't cool, I don't know what is. Okay, so in point of fact, the geologists who did the glaciers and the geologists who did the coast got it right, and an astronomer can confirm it. Okay, so we had fun with that. Jerry Mitrovica is Carling Hay was the lead there. But we're going to run into the future. Okay, so these are IPCC futures. If we don't burn too much, if we burn a lot, and what I'm going to show is that this really might be well on the optimistic side in a hot future. And that's worth worrying about. And so that's what we're going to walk our way through here a little bit. If that's on the optimistic side, this is ice sheets, right? So more or less, all the mountain glaciers on Earth are a third of a meter of sea level. Then we run out. We can't do anything more. The ocean has warmed a couple of degrees since the ice age. You get just over a third of a meter of expansion per degree. It's not absolutely constant, but more or less. And so, but the ice sheets, Greenland is 7.3, Antarctica is more than that. So the question, will sea level rise be large and fast, is a question, what will the ice sheets do? Okay. Now remember, sometimes even a little sea level rise matters. This is New Orleans, this is Hurricane Gustav. Gustav did not get into New Orleans. But what we're talking about is the potential for sea level rise out of this picture. So that's the interesting thing. So let me take you to Greenland. I'm going to do a little paleoclimate from Greenland, a little paleoclimate from Antarctica, and then I'm going to do future physics for both of them. So we'll go to Greenland. I was a little part of this paper from Jörg Schaefer and many other very good people that came out last year in Nature. Mostly I kept poking them to do it. When we drilled at GISP 2 in central Greenland, we pulled up some rock from underneath. That's what's left of the rock. And the rock is laden with cosmogenic isotopes. It's full of beryllium-10 and aluminum-26. Those are made within a meter or two of the Earth's surface. Right now, it's under 3 kilometers of ice. And so it was exposed to cosmic rays recently enough that the radioactive elements made have not decayed yet. So in a geologically recent time, most of the ice was off of Greenland. Not all. There's still a little bit of old ice left in a few places, sort of mixed up in a melange at the bottom. We're not sure exactly how much ice you have to get rid of to get GISP-2 exposed. Different models shrink in different ways. Remarkable lack of agreement. But everyone has agreed that to get cosmic rays there takes losing a lot of ice from Greenland, and that this happened in a geologically recent time. Now, this is the benthic stack down here at the bottom. So 2.5 million years ago is on your right. Today is on your left. You see the ice age cycling. You see the faster ice age cycling. The cosmogenic isotopes so far measured do not provide a unique answer to when it was exposed and how long, but they place very strong limits. If you wanted to say the ice has been there for a long time, you could have had ice cover back a little more than 1 million years, but then you had to have it deglaciated for 250,000 years to get enough cosmic rays. That is the most extreme that you can get. You cannot push the melt back farther than that and be consistent with the data. You could instead deglaciate at all the interglacials, or you could deglaciate at some of the interglacials and have something back here. There's lots of different versions. But you must have deglaciation in a geologically recent time. And if you look where we are today and you look at the warmth that's inferred going back in time, now this is not a Greenland record, this is a global record, but first of all, this does not look like any climate record you ever saw. And secondly, if we make it lots hotter than today, we are going to pass the threshold that took most of the ice out of Greenland. And that's pretty clear, right? One possibility, we published this one, it was one we used to like, we're not sure anymore. If you take Greenland and you warm it just a gnat's eyelash above the temperature for its survival, and then you hold it there. So just move past the threshold and then hold it. It takes, according to this model, 10,000 years to melt the ice sheet. And some of those interglacials are only a few thousand years long. So maybe the ice survived, not because the interglacial was too cool, but because it was too short. And so maybe a little short one like this one or this one didn't melt it, but a longer one like that did. Now, it's worth remembering that if we make it really hot, it melts in 300 years. So hot matters to Greenland. But one possible interpretation is that Greenland does melt slowly, but that we're close to its survival limit. There's no way we have figured out to avoid that too much warmth makes Greenland in big trouble. And then I'm going to take you to the other pole, farther back in time, do another little piece of paleo that I helped with a little bit. As you probably know, there's a lot of evidence that is not found on the table near certainty, but that generally points to high sea levels during the Pliocene at a time when CO2 was not much above where we are now. And that evidence includes things like the del 18O of the benthic stack. You pretty much have to get ice off of Greenland and West Antarctica, and you can have as much as sort of 13 meters off of East Antarctica and still be consistent with the benthic isotopes. So there's evidence that, if you go look at how do you make the ocean isotopic light enough, you melt enough ice, how do you do that? There's a whole bunch of Pliocene beaches. Interpreting them is always complicated. They have been warped by tectonics, they've been warped by isostasy, they are still relaxing from the last ice age, but it's probably easier to interpret them as indicating a lot of sea level rise than anything else. If you go off of East Antarctica and you go get an ocean sediment core, there are pulses of iceberg-rafted debris in those sediment cores. Now, in the modern world, Antarctica doesn't make much iceberg-rafted debris in the cold places because it has ice shelves. And an ice shelf to a geologist is just an iceberg-rafted debris filter. It's just a way to hold the icebergs against the continent until the ocean melts the rocks out. And so the big ice shelves of Antarctica don't make any iceberg-rafted debris. It all falls underneath. But if you go off of East Antarctica, back in the Pliocene, you see these pulses. And those pulses are loss of the ice shelves. And when you lose ice shelves, then you lose ice. And so there's a bunch of things that sort of point to the Pliocene as having a high sea level because you took ice out of East Antarctica as well as West Antarctica and Greenland. So when I was a student, though these many decades ago, Ohio State was all excited. They had gone up in the Transantarctic Mountains and up in the Sirius Formation tills, high on top of the mountains, there were Pliocene marine diatoms, lots of them. And they got all excited, and they had this crazy idea that, first of all, the East Antarctica deglaciates partially, the sea comes in, the diatoms are deposited, then this giant ice sheet grows, and it goes over the top of the Transantarctic Mountains to put the Pliocene diatoms up there. And this was all the rage, and they had camps in the Transantarctics to study this, and they had meetings on it, and it was in the New York Times. And somebody finally said, wait a minute, the diatoms are only in the top of the till. They're windblown. Thank you, we don't have to worry about this. And they threw it, it just sort of disappeared. But if you go to Antarctica today and you ask what diatoms are blowing around, there's no marine diatoms blowing around Antarctica today. Diatoms in the ocean are wet and sticky. They do not blow up on top of the Transantarctic Mountains. The diatoms blowing around Antarctica today come from a few little dry lake beds in the dry valleys, and they come from Argentina. But at some time in the past, there was a big source of Pliocene marine diatoms blowing up on top of the mountains. So if you take Dave Pollard and Rob DeCanto's ice flow model and you set Pliocene, this is what happens. And these brown spots are where the ice deglaciates, the ocean comes in, and then a few thousand years later, the land comes up. And this is the wind field. These are where the ocean would come in, and then the land would come up. This is the wind, and this is the Sirius Formation. And so what do you see if East Antarctica deglaciated to give what you see in the seafloor oxygen isotopic composition, and to give what you see in the high beaches, and to give those iceberg-rafted debris pulses? Then there was a source of Pliocene marine diatoms. And I won't say that's proved, but there's a prediction comes out of these other things that you should see this and they're there. And so what I would say is it's now pretty clear from this work and a lot more that we are close to the CO2 level that, if sustained over long times, will give you 20 meters of sea level rise. It will give you sea level that's higher than 10% of human population right now. But is that orbital time scales, or is it fast? Right? Because that may be 20,000 years, or it may be fast. And so what I want to do is go to fast yet. The problem is we probably have never seen a combination of ice as big as it is today and temperature as high as we might get to in all of history, because nature dialed up sunshine or CO2 slowly, and we're doing it fast. And so we're going to have to do physics. We're going to actually have to do processes. So let me show you this. This is a picture, and Julian Dowdeswell published this in Geology many years ago. It looks like you go to a deglaciated continental shelf, and you look at it, 10K here, and the ice did things to it, and then the ice stopped. And the ice sat there for 1,000 years, thousands of years, and it made these giant morainal banks. And then the ice left without leaving a trace. The ice, it's like an army. It occupies the high ground, and it hangs on for dear life. And then when it retreats, it goes to the next high ground. Okay? And we've been working. There's a dozen papers from our group. There's a whole lot of other things that other groups are doing. They're just fantastic work. A lot of it is done over here. Really good people. And there's work to be done. These are the most wonderful systems. How does it stabilize on those ridges? How does it lose those ridges? Ice shelf, the tides make it go up and down. There's a little inland echo of that that's only a centimeter. But when it goes down, it squeezes the tills and it makes a hard zone. And when the ice flows over that hard zone, it makes bumps. And those bumps then change the water system. And so if you have an ice shelf that's being fed from under the ice, you get channels and water gets pumped in under those channels when the ice goes up on the flexure. And you have something that sort of looks like a lagoonal system with channels going into a lagoon behind a barrier island, except that's compacted till. These are just fantastic systems. There is more geology to be done here. It's really fun. But what it does is it reinforces our knowledge that there are very strong stabilizers that leave the ice at a place for a long time. And when the destabilizers win, it goes somewhere else. Okay? And so that's what this is supposed to say, is that the ice grounding lines stabilize. Occasionally they retreat in an orderly way, but often long time gone. Now, fortunately, usually if you do a retreat event, your Jakobshavn Glacier, your Rink Glacier, whatever, you're the Irish Sea ice stream. Normally a retreat event is only a little tiny bit of global sea level. The worry is that West Antarctica has now gotten itself to a configuration where a retreat event would be 3 meters of sea level. Because everything in color down here in West Antarctica can drain out through that. And once it starts retreating into the hole, there's no bump to stabilize on until it gets to the transantarctic mountains. And so by a purely geometric accident, if this thing seriously destabilizes, or this one, it can take out all the marine basins. And that's a lot rather than a fraction of a millimeter. So these things, that thing that Julian showed you, it was a fraction of a millimeter sea level, but this is serious. Okay? So, ice shelves, right? If you walk down to any of the huge, beautiful Gothic cathedrals, you know they used to have troubles. The roof tends to sag in, the walls tend to bulge out unless you have a flying buttress. Ice sheets are the same way. It's -50 up there. That's not going to melt. But it spreads down to the coast. This remains attached. It's melting there. Every big ice shelf is melting on the bottom, so the IRD goes right there. They run aground on local seafloor highs, or they sit in bays and scrape past the sides. This pushes back on that, which holds that up in the same way that the flying buttress of the Gothic cathedral holds it up. This won't melt. This can. Really easily. Okay? And what one sees, as a review we did a couple years ago, what one sees is that you have an ice shelf system that is stabilized in some fashion. They're melting on the bottom, dropping their IRD. If you turn up the temperature, either meltwater breaks through the cracks, something we've worked on a little, or it melts from the bottom. And when it gets to some thinness, it breaks off. It doesn't just get thinner and thinner and thinner because the tide is flexing this thing. And at some point, it just breaks off and it goes to a cliff. And when it does, you have lost all the drag on the sides of this. This flows faster, that raises sea level, and the thing retreats. Okay? So this is what one is especially worried about. It is primarily temperature, and it's always been primarily temperature. Scott actually thought that the ice was bigger in the past when it was warmer. No, it was bigger when it was colder. The ice sheet gets biggest when it snows least on top because it's controlled so much at the coast. The effect of a 1/10 of a degree change in temperature under a typical ice sheet is more than the effect of 1,000 years of sea level rise on the deglaciation. These are you could kick one with a sea level if you were really, really, really constant water mass, but primarily these are temperature. And if it gets warm above or it gets warm below, they break off. So let me show you this. We're going to go to Greenland. We're going to fly in along the yellow arrow. This is Jakobshavn. Jakobshavn had an ice shelf. The ocean warmed by 1 degree. The ice shelf broke off. The ice flow tripled. Right. So we're going to look in here. Tundra, the ice sheets at the top. This is a deep fjord, and it has icebergs on top, but then deep water. And I'm going to show you 2 pictures. One here, then one here. The one here, it is a deep fjord. There's water under there. Okay, that's a seal. They do oceanography with the seals. They put instrument packages on them, and they swim around and then pull under it. And then eventually, you get the seals down here. And this used to be filled with an ice shelf. This is a 100-meter cliff, 900 meters below sea level. And so this is the Greenland ice sheet. This is water with a little bit of broken up ice and a seal. We flew through Washington on the way over. There's the Lincoln Memorial for scale. Right, this is a 30-story building. It's serious. Next picture's right there. These are 10-story cracks. Okay? I was in a helicopter with senators. The pilot says, "How close do you want to get?" I said, "Those are 10-story cracks. Back off a little." Okay. Right? Okay. And what happens is this thing sits there so you can fly by in your helicopter, and then it breaks. And Martin Trufer gave me these pictures. I did not take them, but so here's your 100-meter cliff. There's the Lincoln Memorial, and here's one breaking. Right. So that's a 30-story building. You are going to see a 50-story high splash. Right. If you've never seen a 50-story high splash, keep watching. This is just fantastic. I'll run it backwards. I mean, we can just sit here and do this. I'm sorry. This is just wonderful. Right? And this makes, you can hear the earthquakes here, magnitude 5 point something earthquakes. And so there's the cliff. And right now, this is tied for being the highest ice cliff on Earth. It breaks, it waits a few months, and it breaks. Now, any highway engineer will tell you, if you make a really deep, steep road cut, you lay it back. Because the deeper it is, the steeper it is, the higher it is, the more likely it is to break, and the faster it breaks, the bigger the stresses. And what we're scared about is if this sucker retreats, it'd have a cliff that's twice as high, and maybe 3 times as high. And if that one is just ready to break, what does a one that's twice as high or 3 times as high do? And we can't ask paleo because it's probably never happened, because it's retreated in cooler conditions than we might get to. But we played really simple parameterizations for this. Rob and Dave put it in their model. And when you do that, after it gets warm, so there's meltwater wedging things open and there's hot water melting underneath, after it gets warm, incorporating these mechanisms accelerates the expected collapse to decadal timescales. And would I bet on this? I don't know. This is new. We've got a couple papers out, but boy, this has not been tested in the way a lot of things have. But if we go to a system that is hotter with more ice than nature has seen, and we make cliffs that are higher than that 100-meter one, I wouldn't bet against it. And so this is a summary. So out to 2100, the IPCC estimates of sea level rise for real fast warming and not so fast warming. NOAA over on our side did some estimates, came up a little higher maybe. This Horton et al. Expert elicitation came up a little higher. But that's before West Antarctica goes. And, I don't think we can tell you with confidence that that can't happen. That's consistent with what we know now. And so what do we know? I mean, the paleoclimatic data, the physical understanding shows that we're close to CO2, which, if sustained, will cause very large sea level rise. And in addition, there is a real possibility that if we make it hot, that the rise will be fast. And it will be fast not just on a geological time scale, but on an economic time scale. And so we've got a huge amount of work to do. Come join us, it's fun, right? But thank you. It has been such an honor and a privilege for me to be here, to join you for a moment. What you do is important. And so I will leave you. I took this picture in or Cindy took this picture on South Georgia. We did doctor the kit on the penguins, but otherwise they really were on the pitch. Thank you.
Thank you, Richard. A fantastic, very scary talk. I'm sure there are some questions out there. Please. Peter.
In the 1980s with BP, we monitored a surging glacier on Spitsbergen, the Buchanan Bean Glacier, and we detected what are called harmonic tremor seismic events, which are indicative of tensile failure. Are you doing any seismic monitoring? Because that can tell you the onset of opening of these tensile fractures.
So my colleague Sridhar Nadakrishnan and I have, he's the expert, he does the monitoring. We have heard outburst floods under the glaciers. So in fact, when the water goes, it gets an echo going in. We can hear the calving events. We also get these fantastic motion events. One of the first realizations that an ice sheet could be very unstable is that as the tide goes up and down on the Ross Ice Shelf, it forces, in part by this flexure and in part just by pushing back, and it causes waves of motion. And those waves propagate up glacier, and you can hear them because they trigger little earthquakes underneath as they go. And they go 100 kilometers in a day and a half. And you say, wow, people used to say, oh, ice sheets will be slow. And then you realize the tide is reaching inland 100 kilometers in that. And so, yes, the seismic monitoring is fantastic. I shouldn't waste your time, but we have a paper, Luke Zoot and Sridhar and I and some others did. As you probably know, there's a nuclear test ban treaty verification monitoring. And at some point, one of their stations started getting these repeating earthquakes every 20 minutes, plus or minus 2. And they called Sridhar and they said, what's going on? And he said, the paper's coming out on that. It's in Nature Geoscience. Because they're actually, the ice stream, one of the big through glaciers in the Transantarctics was making this little earthquake every 20 minutes, plus or minus 3 for a year. And it stopped the entire ice stream, and it would build up, and then 20 minutes later it breaks. And it was modulated a little by the tide. And that may actually be one of the ways that glaciers erode. Because when the earthquake happens, it moves forward about that far, and the water pressure in the cavities in the lee side of the bumps would go to atmospheric, but the water pressure in the rock would still be at 170 atmospheres, and that'll hydrofract. So yes, absolutely, absolutely. So yes, it's really important, really fun. Thank you.
Colin, just wait for the microscope.
Sorry, yes. Within the society, is that? Yeah, working, okay. Within the society, we do have some of our fellows who consider that the rise in temperature since the end of the Little Ice Age is completely natural. Now, what would you say to them?
Yes, simply, no, right? So we know, right? So the Little Ice Age ends. The Little Ice Age is fairly clearly a random clustering of big volcanoes blocking the sun, and a little bit of dimming of the sun, and then a dynamical response in the ocean atmosphere system that was especially amplified here. So where our history for many of us came from is in northwestern Europe, and the signal was really big here because of changes in the ocean. So it's this combination of sun volcanoes and response to that. It ends in part because we're contributing radiative forcing from CO2, and in part just because nature. And so in the early 20th century, nature is trying to warm it up. In the late 20th century and into the 21st century, nature is trying to cool it off. So we have been watching the sun with satellites for 30 years, and that 30 years, the sun has dimmed a little bit. The warming comes up where nature and humans are pushing the same direction. When nature starts pushing down and humans keep pushing up, what happens? The temperature goes up. And so it becomes very clearly a human signal because nature most recently has tried to go the other way. It's a much longer answer to walk through all the other pieces of it. But in the end, what you'll find is very, very clearly that we're now primarily in charge. And nature sort of wobbles around a little bit. The sun, when the sun changes, climate changes immediately, directly, but the sun doesn't change much, except very slowly. And the volcanoes, there's no way for a volcano in Indonesia to tell a volcano in Alaska it's time to erupt. So they are random and they matter. A big volcano gives you a good chunk of a degree for a year or two, but it's a noisemaker. It doesn't get organized. We have high confidence that cosmic rays don't do anything strange. The Lechamp event 41,000 years ago, the magnetic field goes essentially to zero. The cosmic rays come streaming in. They make beryllium-10 and radiocarbon. If you look in the ice core, beryllium-10, whee! That's the Lechamp event. Climate. We can't see it, right? And so once you get all of these pieces together, right, orbits are hugely important, but there's 1,000 years, they don't matter. It takes several thousand years to matter. 100 years, nothing. And so once you get all the pieces in, the more history you know, the more we look important.
Thank you. Really enjoyed your talk. I just wanted to hear your opinion. There's a term that we've come up with, which we call 2100-itis. And I noticed a lot of your plots kind of finish in 2100 for obvious reasons for policymakers. But a lot of these changes that you're talking about are irreversible. So at what point, do scientists have a duty to, get that across to the public?
Yeah, we do. And I think it's important. You know, and you have dealt with this, and I know that to an economist, generally, and Lord Stern is a wonderful, notable exception, but and a few others, but normally, what they do is they say that your grandchildren are going to be incredibly more wealthy than you are. You do not want to deprive yourself to help them very much because they're going to be so much richer and you're so poor. The money that they get from you will allow them to solve problems that you don't bother to solve now. And they are not quite as important as you are anyway, right? That is called the pure rate of time preference. And if you make those assumptions, we would be economically better off if the world were taking more actions now to reduce climate change, but not by a lot. If you relax those assumptions, if you really sort of say, wait a minute, it is not right for me to say that I'm more important than my grandchildren, just because. And maybe money won't solve their problems, and maybe they won't be richer than me. Then the answer would be we would be doing a lot more to head off climate change. And so that for the policymakers, the short term usually comes up, but it doesn't have to be that way. The policymakers, in large part, eventually reflect a lot of what we do and what we vote and how we speak. And if our world were to say, we don't want to leave our grandchildren London underwater, they might change what they do. And I think you've been one of the leaders, so I'm talking to the choir here. Yeah.
Time for a last question, over on the far side.
How do you think you can convince your executive branch that this is not Chinese fake news?
Yeah. It is a fascinating problem. You raise a big problem. I don't have them loaded, but if one gets maps of the United States by county, they have now done surveys of what United States citizens think about climate change, and they'll give you the map by county. And if you ask, is the climate changing, the majority of Americans will say yes. But you can see this pattern that the coasts and the big university cities are different from places in between. If you ask if humans are causing it, it's exactly the same pattern, but it's shifted down. Less belief that humans are causing it. If you ask, are scientists agreed on this? Right? about half of Americans would tell you that scientists agree that CO2 is a greenhouse gas that causes warming. And that was something that was purchased, right? Somebody bought confusion. And a lot of very, very good people are confused because somebody was very efficient at feeding them a very confusing story. If you get to, though, the last two of these maps, one of them is, even though we've just had people tell us it's not a problem and we're not causing them, if you then ask, are there good solutions to it? Virtually every American says yes. The problems that they don't believe in, they believe they can solve just fine and it will help. And all of a sudden you realize that a lot of this is people who are worried about different things. And the confusion feeds into that, but there's more in play here, because when you ask about solutions rather than problems, this. And then the last map, are you talking about it with your neighbor? They're not sure if it's a problem, they all believe we can solve it, and nobody's talking about it. Okay. Now that's where we've heard several of you who are outreach experts. All of you have to be. We have to make this knowledge useful. And that's more than just getting the knowledge out there. And I don't know how to do it, but I suspect that we do. And I know that you and you have been doing well on this and are in the lead. And that's the answer, isn't it?
But more of it.
Now, more of it. Okay.
Great, Richard. Thank you very much. Thank you.